a look at analyzing runtime of algorithms. So this is a very important concept that we'll see a lot in the world of computer science. Many times we describe algorithms by these types of notations. The most common one we'll see is something called big O notation. And so we'll see that, oh, this algorithm's O of n squared, or it's n log n. And that just tells us how efficient an algorithm is. So for example, an O of n algorithm is more efficient than an O of n squared algorithm. And this has to do with asymptotic growth. So how quickly do these functions grow? If you imagine the graph of if we were to graph n, that would just be a straight line. All right, let me just draw a quick sketch before we dive into it. So O of n would be like a straight line if we were just graphing n. N squared, that's quadratic. So that looks something like this. Square root of n is something like this. So there's different types of graphs that we have, and we can see that like the n squared graph, that grows much quicker than the n graph. So what we're graphing here is this is, the x-axis is our input size. So that's like the letter n, how large our input is, and the y-axis is time. So if an algorithm is O of n squared, as we get to larger and larger input size, the time grows much, much faster. Whereas if it's O of n, well, then it's just a linear growth, which is okay. And then some of these smaller functions are a lot nicer. So that's sort of what we mean, but let's just describe it a little bit more clearly. So there are three types of notations that we should be familiar with. The first is big O, and that's the most popular one. And there's also big omega and big theta. And oftentimes, we will see that when people say big O, they actually mean big theta. So that's kind of confusing, but it's all right. So a function is O of another function. So f of n is O of g of n. If there exist constants, c and n naught, that are positive, such that 0 is less than or equal to f of n, which is less than or equal to c times g of n, for all n greater than or equal to n naught. So that means we choose two constants, and if this inequality holds for all values greater than our n naught constant, then it's big O. And if you want the limit definition, f of n is equal to big O of g of n if you take the limit as n approaches infinity and the quotient of the two functions is equal to 0 or a constant. So that's that. Next is big omega. So f of n is big omega of g of n if we have these constants again, such that 0 is less than or equal to c times g of n, which is less than or equal to f of n, where for all n greater than or equal to n naught. So very similar definitions here and here. It's just the order of these two are flipped. And the limit definition is that the quotient should equal infinity or a constant. So for big O, we can think about this as like an upper bound, because we're finding this like function c times g of n, which is always greater than our function that we're looking at, f of n. It's always greater than it. So it's upper bounding f of n. And then big omega is sort of like a lower bound. And then big theta is, well, now we have these three constants such that f of n is sandwiched in between g of n times two different constants. Once again, for all n greater than or equal to n naught. And so this property holds, it's big theta of g of n, if it's both big O of n and big omega of n, g of n. And by the limit definition, if you take the quotient, the limit as n approaches infinity of that, if it's equal to a non-zero constant, then it's big omega. And that just comes from the fact that it has to be, it's big theta. And that comes from the fact that it has to be both big O and big theta. And if we look here, big O is when the quotient equals 0 or a constant. omega is when it's equal to infinity or constant, so the intersection is constant, which is here, and it has to be non-zero. Okay, kind of difficult to understand with all of these numbers and things, so it really helps to do some examples. So let's just go through a couple of examples right here. All right, so first we're asked to show that n squared divided by 7 minus 30n is equal to big theta of n squared. So that means we need to show two things. First, we need to show that it's big O, and then we need to show it's big omega. So let's let f of n equal n squared divided by 7 minus 30n, and g of n is equal to n squared. All right, so first we want to show, I abbreviate it as WTS, that f of n is equal to big O of g of n, which means that we want to find constants such that this relationship holds for all n greater than or equal to n naught, where c and n naught are like positive numbers. Okay, so well, let's try to draw it out. Do I have a different color I want to use? I'll use green. So we want a less than or equal to relationship. So f of n is n squared divided by 7 minus 30n. And we want that to be less than or equal to some constant times n squared. Okay, so when we're just starting out with this, it can be kind of difficult to figure out what this constant c should be. But let's think about a little bit what we explored previously. When we graphed n squared and n, we saw that the n squared term grew a lot faster than the n term. So this is sort of like our dominating term on the left-hand side, and on the right-hand side it's also an n squared term. So here the constant is like 1/7 times n squared. So if we want this left-hand side to be less than or equal to this right-hand side, our constant c should be like relatively big. Meaning it shouldn't be something like 1/14, because 1/14 is less than 1/7, and we want this side to be greater than this side. So we can choose c to be like anything really. We just need to show that there exists constants such that this relationship holds. So I'll choose something big. Let's choose, yeah, I'll use a different color. Let's choose 10, right? That seems big enough. And let's just try to show that this relationship holds. We also have to find our constant n naught. So we're going to say that this holds for all n greater than or equal to some n naught, which we have to find. Well, let's try to solve this. So, let me just... Okay, so this left-hand side, I don't like the fraction, so I'm going to multiply both sides by 7. We get n squared minus 210n is less than or equal to 70n squared. And then we can subtract an n squared on both sides. We'll get 69n squared is greater than or equal to 210n. We can cancel an n on both sides and get 69n is greater than or equal to 210. And then we can, do our division or whatever. Sorry, wait, this should be a negative 210. We can do our division and we'll see that n is going to be greater than or equal to some negative number. But, I mean, sure, that's fine. So I can just say that, like, let's let n naught equal 1. Right? So if we put n naught equals 1 here, then we can check if for any value greater than or equal to 1, if I plug that into n, will this relationship hold? Would c equals 10? And sure enough, it will. So for c equals 10 and n naught equals 1, we have shown that f of n is big O of g of n, right? So that's good. So now we want to show big omega. We want to show f of n is equal to big omega of g of n, which means that we want to find constants such that this relationship holds for all n greater than or equal to n naught. All right, so let's sort of write out what this is saying. So our relationship now is c times g of n, which is n squared. We want that to be less than or equal to n squared over 7 minus 30n. So remember before when we were choosing our c on the right-hand side, we wanted it to be pretty big because we wanted this side to grow quicker than this side, and we saw that there's this 1/7 coefficient on the left side, so we knew we wanted something greater than 1/7. Here, we want this side to be smaller than this side. So it makes sense to choose a smaller c such that c is less than or equal to this 1/7 term. And since c could be anything, well, let's just play it safe and choose something kind of small, like small enough. So I'm going to choose c equals 1/14 because it shares it's a multiple of 7. 14 is a multiple of 7, so I'm hoping that that will help us in our simplifications. So this will give us 1/14 n squared is less than or equal to n squared over 7 minus 30n. For all n greater than or equal to some n naught, we still have to find that, and we still have to define that in order to say that it is big omega. All right, so let's continue with this. We can subtract n squared over 7 on both sides, and we'll get negative 1/14 n squared is less than or equal to negative 30n. We can divide by negative n on both sides, and that cancels a negative sign and one of these n's, and it also flips the inequality. So we get 1/14 n is greater than or equal to 30, which tells us that n should be greater than or equal to 420. All right, so let's use that for our n naught. Right, if we say for all n greater than or equal to 420, does this relationship hold? And well, you can test it out, and sure enough, you'll see it does hold. So we can conclude for c equals 1/14 and n naught equals 420, we have f of n is equal to big omega of g of n. All right, so we're almost there. We're almost there because we want to show big theta, and we've shown big O and big omega. The thing is, the way we defined big theta is that we needed like 3 constants, c1, c2, and n naught, such that this holds for all n greater than or equal to n naught. And so the thing is, like, we found one constant c, which is fine. We found another constant c, which is great. It's just our n naughts differ. Well, we can remedy this pretty easily. If up here we have n naught equals 1, we've said that this relationship will hold for all n greater than or equal to 1. Well, it will also hold for all n greater than or equal to 420, right? Like, pretty self-explanatory there, that if it's greater than or equal to 1, it holds true, then greater than or equal to 420, it will hold true. So we can adjust what we set up here and say instead of n naught greater than 420, or than 1, we'll say n naught greater than or equal to 420. And then we can see that, we can conclude that 0 is less than or equal to 1/14 times g of n, which is less than or equal to f of n, which is less than or equal to 10 times g of n, for all n greater than or equal to 420. So we found those constants, we've shown this relationship holds, so therefore we can conclude that f of n is big O of g of n. So it's a nice conclusion, but let's just take a moment to analyze what this means. This was our f of n, and this is our g of n. So the big takeaway here is that in the future, we don't really want to be doing all of this math just to show that this is theta of n squared. In fact, we can sort of just look at this and know it's going to be big theta of n squared. And the way we do this is sort of just by looking at which terms dominate. So this 30n, while that is like a relatively large quantity, the n squared term dominates the left-hand side. And what that means is as n gets larger and larger, this n squared term is going to grow super quickly that this minus 30n isn't going to change it that much. So on the left-hand side, this is like the most important term that we have to consider. And then when we have a constant times that n squared, constant doesn't affect it whatsoever. So really, k times f of like n is going to be equal to big theta of f of n. So here we have 1/7 times n squared. So 1/7 is k, f of n is n squared. So that will be equal to big theta of n squared. So this kind of thing comes with a little bit of practice. But soon enough, we'll be able to just look at this and be like, okay, we can ignore this term, and we can ignore the constant. The main term here is n squared, so it's big theta of n squared. So that's the first example. Do I have another one? Yes, I do. Okay. So we're going to show that log base 2 of n is big O of n. And we're going to denote log base 2 of n as Lg of n. And I'm still going to pronounce this as log n. It's just that a lot of things that we do in computer science, the logarithm is base 2, so we'll just denote it as something a little bit differently, and it'll be fine. Actually, before we do that, let's just go back to the previous example. I just want to show it with the limit definition. So if we take the limit as n goes to infinity of f of n divided by g of n, let's just plug in what those f of n and g of n were. So f of n was n squared over 7 minus 30n. G of n was n squared. We'll multiply the numerator and denominator by 7. N squared minus 210n over 7n squared. And if we remember how to evaluate limits, when we have this fractional term, both the numerator and denominator are polynomial, we look at the highest degree term of the numerator, which is this n squared term. We look at the highest degree term of the denominator, which is also n squared. Since their powers are equal to each other, we take the ratio of their coefficients. So this would be 1, this would be 7. So we conclude that this is equal to 1/7, which is a non-zero constant. Therefore, it is big O, or big theta, by our definition here. You'll notice that I'm using big O and big theta interchangeably because almost everyone calls big theta big O. It's just like the colloquial term for it. Okay, let's go back to this. We're going to show that log n is O of n. And in fact, it would also be cool to show that log base 10 of n is equal to big O of n. And this is true, and you can prove it to yourself after we do this. It'll be very similar. So we're going to prove this by induction. So proof by induction. Okay. So the way we're going to do this is we will show that log of n is less than or equal to n, right? So we want it to be upper bounded by n. For all n greater than or equal to, we have to choose our n naught. So let's just try 1. And if it doesn't work, we'll see that in our base case. So let's start with the base case of when n equals 1. Then we have a log of n is equal to log of 1, which is going to be equal to 0. And then n is simply equal to 1. So is log of n less than or equal to n? Well, 0 is less than or equal to 1, so the base case checks out. So we're good. Next, we'll move on to the induction hypothesis. So that's the IH. And here we're going to assume that log of k is less than or equal to k for k greater than or equal to 1. Right, so that's the induction hypothesis. Next is the induction step. And we want to show that log of k plus 1 is less than or equal to k plus 1. And we want to use our induction hypothesis somewhere in there. This can actually be kind of tricky because it's we have to be kind of liberal with it. In normal mathematics, when we do induction, we're typically very strict with how we do things, but since we're dealing with inequalities here, we can be very free with how we do certain things. So log of k plus 1, I can say that that is less than or equal to log of 2k. Because, well, if k equals 1, then on the left-hand side we have log of 2, and on the right-hand side we also have log of 2. But then if k is like 3, then on the left-hand side we have log of 4, on the right-hand side we have log of 6. So this 2k term grows quicker than this k plus 1 term, so this left-hand side will always be less than or equal to this right-hand side. So with that, we can do a simplification. Using our log rules, we know that this is equal to log of k plus log of 2. Okay? And by our induction hypothesis, we know that log of k is less than or equal to k because that's what we assumed. So this will be less than or equal to k plus 1. So that means log of k plus 1 is less than or equal to k plus 1, which is what we wanted to show. So that concludes the proof by induction. So therefore, log of n is less than or equal to n for all n greater than or equal to 1. Therefore, log of n is big O of n. So that's our neat little proof by induction there. One of my favorite proof techniques. Wonderful. So that will finish our analysis of this asymptotic growth analysis. And next we're going to take a look at how to analyze runtimes with actual code.